In this video, we're going to take a deeper look into the cross product formula and figure out a way to get a clear answer if our object is on the left or on the right. From the last video, we know the right hand thumb rule will tell us the direction, but we can't feed in our right hand into Houdini and call it out in a wrangle. Or can we? Is there really a right hand vex function? That's where we left off in the last video. I need a simple way to implement this in order to complete our left-right detector. This is a direct continuation from the previous video, basic concept number 4, left or right, where we covered most of the cross product, vex code setup, and covered how to calculate the relative vectors that we need. And now we're going to take it up a notch by adding a bit more complexity. This video covers the math knowledge you need to complete our project. If you're only concerned about the vex code in Houdini's wrangle node, then you might want to skip to the next video. That's where I write out the vex code and you'll get to see the left-right detector in action. This video is mainly to enrich your background knowledge so you may apply the basic concepts in any other project. Now this also brings us to the next problem. How do we know that the cross product is pointing upwards or downwards? When we take the cross product of two vectors, it returns the perpendicular vector or orthogonal vector as mentioned many times throughout this miniseries. But did you know what happens when we take the cross product of 2D vectors? Up until this point, I've only talked about 3D vectors because Houdini is a 3D application. If we take the cross product of 2D vectors, we end up with a scalar value. Probably because 2D vectors are all flat on the same surface. So the perpendicular vector of the same flat surface is probably not as interesting as 3D vectors. What is interesting is that cross products of 2D vectors gives us the area of a parallelogram formed by the two vectors. It's like that invisible triangle I did in basic concept number 3. After connecting the dots, you'll see the triangle, or in this case, if you connect the dots, you'll see a parallelogram. This is the formula for the cross product of 2D vectors. This returns a scalar value and it's the area of this parallelogram shape. We'll make a small change to this formula because we're only concerned about the directions of the objects and we don't care about the actual magnitudes. I want this formula to return a positive or negative value depending on which side the sphere is on, left or right. The absolute function just takes the sign away, so we don't want that. And the sign function is always positive, but I don't care about the magnitude. So we'll remove the absolute signs and the sign function because none of these will determine a negative or positive value. We are left with multiplying two vectors. Both vectors are 2D. So this is basically multiplying a square matrix. This reminded me of the determinant of a square matrix, which conveniently gives us the signed area. Signed area. That's exactly what we need because we're looking for a clear positive or negative value that will tell us if the sphere is on the left or right of the robot. Let's see what this looks like on our graph. What does this value actually mean in math? The value is trying to tell us if the area of the parallelogram is overlapping the positive or negative coordinates on the Cartesian system. How is this useful for us in that left-right robot scenario? The cross product only calculates the area when dealing with 2D vectors, but our robot is sitting in 3D space. What we can do is project the 3D vectors onto a flat plane, which will convert it into a 2D vector, and we'll be able to use that area formula. The projection formula does complicate things a bit, so I've simplified things for this project. I simply took out the y value of the robot and sphere vectors. It's only possible because my robot and sphere are on ground level anyways, and nothing's really flying around. So the y values are always 0 anyways. Simply removing the y value from everything will do the same projection and get us the correct projected direction. Then we have our 2D vector. Please note, this is not the proper way of calculating projection. The projection formula is out of the scope of this video, but I do plan to cover it in future videos, so stay tuned for that. My simplistic way of converting 3D vectors to 2D will get us the correct direction, which is all we really need for this project, but simply removing the y value will get incorrect magnitude values. It just so happens we don't need the magnitude to determine the left-right direction. Let's run it through the formula and see what happens. The blue vector is the front vector of the robot, and the yellowish-orange vector is the relative vector of the sphere to the robot. We can start plugging in the values. I've already removed the y value from both vectors, but since both vectors are still on the ground, the y value is 0 anyways. Using the determinant formula, I'll get the signed area formed by that invisible parallelogram. Our result is positive and the sphere is on the left of the robot. Let's try another example with the sphere on the right. Again, plugging in the values. We'll see the result is negative this time, which makes sense because the sphere is now on the right of the robot. One last example. Let's move the sphere right in front of the robot, and I want to see what the value for the signed area will be. Again, plug in the numbers, and after completing our calculations, we find that the value is very close to 0. I have to admit, I had to cheat this one a little bit because it was really hard getting the sphere exactly in front of the robot. So the result is very close to 0. Now we know the 0 value means the sphere is straight ahead of the robot or in front. There we have it. We can use this method as a left-right detector. Now we have a basic understanding of the math behind the cross product. We also understand how to use some of the tricks we just learned to create a left-right detector and complete the robot and sphere scene. I didn't know what to release as a digital asset for my Perk members, so I came up with a small vex function for the signed area formula. This goes back to the intro of this video where I questioned if there was a right-hand rule vex function. I don't believe there is, so I went about creating one. It'll be available for my Perk members. It will be called something like cross product 2D, and will return the normalized vector direction, magnitude, and string label of the cross product. This will be a nice handy function available to use in a compact form. Nothing really new, other than the fact I've compacted everything from all of Basic Concept 4, parts 1 through 3, into a nice vex function, rather than a bulky vex code you've seen in the videos. This will come in handy for those of you that have other use cases in other more complex projects. Who knows? You may want to calculate the direction of each crowd agent and make them constantly turn left around a moving animated ball, or use it for a shader coding, making the grass greener on the left of the building where sun shines the most. The possibilities are up to you. We're almost there. The next video will finally be the last video for Basic Concept number 4. We'll start implementing the signed area formula shown in this video, and we'll be writing all the vex code as well. I'll also be adding some more features to the code, and we'll be able to tell if the sphere is straight in front of the robot or straight behind the robot. The next video does have a small portion of math, but it's mostly about vex code implementation. Thanks for watching and sticking to the end.